What specific problem does the Hogwild inference method aim to solve in the context of parallel reasoning for LLMs?
The Hogwild inference method aims to address the limitations of existing parallel reasoning strategies for large language models, LLMs, by allowing multiple instances to collaborate dynamically without a predefined framework. Traditional methods often impose rigid collaboration strategies that can lead to inefficiencies, especially when one thread requires more time than others, causing delays and wasted computational resources. Hogwild Inference enables LLMs to generate tokens in parallel while immediately accessing each other's progress, allowing them to adapt their collaboration strategies on the fly. This flexibility is crucial for solving complex reasoning problems where initial plans may be flawed or incomplete, as it mimics the dynamic nature of human collaboration. Ultimately, the method seeks to enhance both the quality and efficiency of LLM reasoning by leveraging emergent collaborative behaviors among instances.
How does the proposed Hogwild inference method work? Illustrate the key steps of the methodology involved in this approach.
The Hogwild inference method operates by allowing multiple instances of the same LLM to collaborate dynamically without a predefined framework. Key steps include running these instances over a shared key-value (KV) cache, which enables concurrent cross-attention, allowing each worker to access and utilize the tokens generated by others in real time. The method employs a custom cache layout that can be rearranged on the fly, ensuring that each worker can see the latest tokens generated by their peers while maintaining their own reasoning paths. Additionally, the LLMs are prompted to collaborate by providing system prompts and in-context examples, along with specific queries to check for redundant work. This approach facilitates emergent collaborative behavior, where LLMs can adapt their strategies based on the ongoing progress of their counterparts, ultimately enhancing the efficiency and quality of problem solving.
Can you provide a simple yet illustrative example demonstrating how Hogwild inference operates with multiple LLM instances and their interactions?
Hogwild inference operates by allowing multiple LLM instances to generate tokens in parallel while sharing a key-value (KV) cache, which enables them to access each other's progress. For example, consider two LLM instances, Alice and Bob, working on a problem. As Alice generates a token, she can see Bob's previously generated tokens in her KV cache, and vice versa. This means that if Alice realizes that her current task overlaps with Bob's completed work, she can pivot her strategy accordingly. The instances can also agree on how to split the work initially, and if one finishes early, they can check on the other's progress and assist or adjust their tasks as needed. This dynamic interaction allows for a more flexible and efficient collaboration compared to traditional fixed strategies.
What are the theoretical or practical benefits of using the Hogwild inference method over traditional parallel reasoning approaches?
The Hogwild inference method offers several theoretical and practical benefits over traditional parallel reasoning approaches. Firstly, it allows multiple LLM instances to collaborate dynamically without a predefined framework, enabling them to adapt their collaboration strategies on the fly based on real-time progress, which contrasts with fixed methods that can lead to inefficiencies when plans change. Secondly, by utilizing a shared key-value cache, Hogwild inference minimizes computational overhead associated with re-encoding tokens, thus improving hardware utilization and efficiency. Additionally, preliminary experiments indicate that LLMs can effectively coordinate and leverage each other's partial progress, enhancing problem-solving capabilities, especially for complex reasoning tasks that do not fit rigid parallelism frameworks. Lastly, the method demonstrates emergent collaborative behavior, allowing LLMs to detect redundancy and pivot strategies, which is not typically achievable with traditional approaches that rely on independent or strictly role-based interactions.
How is Hogwild inference validated or tested in the experiments? What metrics or benchmarks are used to assess its effectiveness?
Hogwild Inference is validated through a series of preliminary experiments that assess its performance on both simple synthetic tasks and more complex reasoning problems. The initial evaluation involves using the QWQ32B model to solve problems from the GSM-8K test set, where the average fraction of problems solved is reported as a metric of effectiveness. In these experiments, the performance of Hogwild Inference is compared against a sequential generation baseline, specifically measuring the accuracy of answers returned within a token limit. Additionally, for more challenging tasks, the effectiveness of different cache layouts, contiguous, interleaved, and combined, is evaluated to determine their impact on collaboration and problem-solving speed. The results indicate that Hogwild Inference allows for faster problem-solving compared to single-threaded approaches, with metrics focusing on accuracy and efficiency in generating correct answers.
What limitations or drawbacks have you identified in the Hogwild Inference approach, particularly regarding its applicability to different types of reasoning problems?
The Hogwild Inference approach has several limitations, particularly concerning its applicability to different types of reasoning problems. One significant drawback is that it may not be effective for problems requiring strict sequential logic, as these tasks have low potential for parallel gains due to their inherent dependencies. Additionally, while Hogwild Inference allows for dynamic collaboration among LLM instances, it introduces non-determinism, meaning that the final output can vary based on timing interactions between parallel threads, which could lead to inconsistent results. Furthermore, the effectiveness of this approach may vary across tasks. For instance, reasoning problems that can be decomposed into independent or semi-independent subtasks may benefit more than those that do not fit this framework. Lastly, the prompting strategy used to elicit collaboration may not be optimal, indicating that further refinement is needed to enhance the model's collaborative reasoning capabilities.